Alright, so now we can do the answers to the weekly test 3. In general, you guys did not do very well at all at this, which of course concerns me, but I think the reason is that you really just haven't really studied the material. The first question was just a simple one, just to make you remember what the difference is between an enantiomer and a diastereomer. And unfortunately, not a lot of you are kind of getting that. A enantiomer is a structure where the chiral centers are all reversed, and a diastereomer is where one of the chiral centers are reversed. So if we just, for example, leave the OH like this, then the methyl group, we would change from being down to up. Some of you drew this as a wedge. That's not a wedge, that's a cyclopropane ring, all right? A wedge is fully colored in, all right? If you did that, then you would have got your mark. There's just one mark associated with that. All right, this question over here, had you, you need to kind of think backwards of how you would do this. And the problem is if you look at the product, you see that this is the bond that we are needing to form. So if we break that bond, what we need is an electrophile that looks something like this. So there needs to be a leaving group on this carbon. So, well, the easiest one to do is to put a bromine, but chlorine and iodine would probably be fine. But the problem is we need an enolate of an aldehyde. We want this. All right, we want something that looks along the lines of that to react with that. Unfortunately, if we form this, it's going to self-condense. And so we have to come up with another method in order to get this to react with that, because we can't do that. And there are a couple of ways that would have worked. My preferred method would have been via the aza enolate. In other words, we would have, let's just do this here. We would have first reacted with a sterically hindered secondary amine, which would have formed the imine, all right, and we should be able to do the mechanism of that. And once we've done that, we then need to deprotonate this position, all right, using a strong base. So step 2 would have been using a strong base such as LDA. We would have ended up with something that looked like this, all right, with a minus. This is the equivalent of what we wanted but we couldn't make, all right. This over here is the equivalent of the enolate. This can now do the reaction when we add, third step, our benzyl bromide to the reaction, and so that can react now. All right, and we can then, the last step is to hydrolyze the imine that is formed, and so there needs to be a fourth step, which will be adding water, adding a bit of acid, weak acid, to get that to occur. All right, so it's actually a 4-step process for the aza enolate. I would have also accepted if you had said, let's do an enamine. In other words, first step would have been adding some sort of secondary amine, preferably something like this, the pyrrolidine. And then the second step would have been adding the benzyl bromide. And the third step would have been just hydrolyzing again with acid. All right, these are just not, enamines are not as reactive. So in other words, what we're going to react with that would have looked like this. But remember that the enamine is not as reactive as the aza enolate. However, this is a very reactive electrophile, so in this case, it probably would have worked. All right, well, it's a bit sterically hindered, but yeah, that's besides the point. Okay, so that was that answer there. Then this was an aldol condensation, and I saw a lot of weird and wonderful answers to that one. We only did that in the class before, and so we have this. which is we're going to get to react with this aromatic aldehyde. And I really don't want to go into, guys, some of the weird answers that I got for this one. And the conditions are under acidic conditions, and then there's some solvent, water and ethanol, all right? But because it's under acid conditions, we are going to form the enol, all right? It's an equilibrium. We form the enol, which only has one kind of direction that it can form in. All right, this ketone, it can't go on that side, so it has to be on this side. And the enol, and this can do nothing either. You put acid in with this, and nothing can happen to it because there's no alpha hydrogen there. This is perfectly stable. So this will form. Once this forms, we can now use this as our nucleophile and go to that. All right. And there's also H plus around, so that also helps to activate the aldehyde for this reaction. And we end up with H is the tertiary butyl center, new bond to what was the aldehyde, and now to the aromatic ring. All right, so some people actually kind of stopped there and gave this as the answer. But in aldol reactions, remember, under acidic conditions, it's almost always going to do the elimination reaction. And so we can do a proton transfer. We can pick up a proton. Maybe this one disappears and goes onto there, or maybe another proton comes in from somewhere else. I don't know. But essentially, we just want to take a shortcut. We can show that happening. So we protonate it, and then it can leave in an E1 mechanism because this is under acidic conditions. So we've got an OH2. There's the aromatic group there. This is the T-butyl group, and this can leave. And then once it leaves, let's do it stepwise because that's how it happens. It's E1. The plus there, aromatic ketone. All right, so we have a carbocation over there, and now one of the protons there can be picked up by the water that was given off, and the water that's in the reaction, or the ethanol that's in the reaction, and goes to form the double bond. So our product is the unsaturated. There's the aromatic, and I'm just shortening it to make that a bit faster. All right, so that would have been the product of that reaction over there. The next one was also not done very well. The important thing to note is, obviously, this is going to be our nucleophile. There's our electrophile. Using sodium methoxide to balance with this ester over there. But it's the double steps afterwards which are important. And so CO2Me, CO2Me. Methoxide picks up the proton. Boom, that goes in towards that to form the enolate. Let's just draw that out properly now. OMe minus OMe, and we now react with the electrophile. A lot of you, some of you made this mistake with the electrophile where you were losing the carbons, and so be careful of that in the product, that you don't lose your carbons, and so some of you lost some marks from that. Right, so bond goes to that one, like that. All right, 1, 2, 3, 4 carbons, then goes to this. 1, 2, 3, 4 carbons goes there. There's that bond that was formed. Bromine was kicked out. Connects with the sodium, was part of the sodium methoxide, forms sodium bromide. It's a spectator ion that gets out of the thing. Some of you gave this as the answer. We're only halfway because step 2 is adding sodium hydroxide. Sodium hydroxide is going to hydrolyze the esters. So cut, changing this into H. changing it into OH, sorry, OH, OH, all right, makes them into acids. And then the second step, all right, is the decarboxylation. So once you've got the decarboxylation, let's just draw that out now. OH, OH, and there's this funny thing there. So we add some acid to it, which just it can go into a lot of different. We can do quite a lot of arrow pushing over here, but essentially, what gets the correct arrow push for this, it gives us the answer is that CO2 gets given off. So this goes in like that. Instead of it bouncing up over there, it bounces across here because this can be picked up by that proton over there. And so we are left with boom, OH, OH, and all right. And of course, this is just can tautomerize back to the carboxylic acid. Back and pick up a H plus. All right. And so the product looks like that. Okay. Mechanisms, 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 over and over again. The last one was just a simple mechanism of the enamine reaction. This you can go and pick up in your textbook. That's pretty much all I want to say for now. I'll draw out the mechanism for you, but for most of you, you should be able to just pick that up from the textbook. So while I'm doing this, let's get some tunes going, and we'll draw this out. It's magic. Acid. Lone pairs. Plus. I don't need it back. Here we go. Oh, I ran out of space. You get the picture. Yeah, whatever. Alright, that's it.